Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stepp, and I thank you for joining us for tonight's program, Bionic Being, the New Prosthetics. Our guest tonight is Shawn Kelly, an expert on the design of electronic retinal implants for the restoration of vision. Because of his work in one of the most challenging areas of prosthetics, Dr. Kelly is an ideal guide to today's prosthetics generally, and a person who can explain the significance of these developments for the future of the human body. Shawn Kelly has been committed to the design of electronic implants for a long time. He started when he was working on his master's in electronic engineering at MIT, and he developed his ideas further during his PhD research at MIT. The electric eye innovation, or his electric eye innovation, made Time Magazine's 50 Best Inventions list of 2009. Dr. Kelly's work has continued to focus on the development of new medical technologies, and especially on implant systems such as neural simulations. Today, he's a research biomedical engineer at the VA Center for Innovative Visual Rehabilitation and a visiting scientist at MIT's Research Laboratory of Electronics. And as a member of the Boston Retinal Implant Project, he continues to perfect the retinal implant. This past fall, Dr. Kelly honored us with a presentation on the challenges of restoring vision and how the electric eye has addressed that difficulty. That video is on our website. Just look for the electric eye on the page for tonight's lecture. Tonight's presentation, however, addresses the field of prosthetics more broadly. What body parts and functions scientists are restoring and replacing, and what it signifies for the future of the human body and human well-being. It is a great pleasure to welcome back Dr. Shawn Kelly.
Thank you, Yvonne, for the warm introduction, and thank you for having me here again. This is the Bionic Being, the new prosthetics, the new prostheses developed for the human body. So, what is a prosthesis? A prosthesis is an artificial device that replaces the function of a missing or damaged body part. There are two pieces of that that are very important. One is that this is an artificial device. So we're not talking about transplanted body parts, transplanted organs. We're not talking about stem cells or gene therapy. These are artificial man-made pieces that go in the body, and I don't say they replace the body part, they replace the function of the body part. This is important. I work with some very talented scientists and engineers. There are tremendously talented scientists and engineers at companies and research groups throughout the world developing these things, but we just cannot get them quite good enough to completely replace the body. It's never going to be as good as what was there, but we can help people who have this kind of damaged or missing body part in a variety of ways. Let's talk a little bit about the history of these devices, the history of these prostheses. It's thought that as early as 4000 BC, ancient Egyptians tried to replace legs, replace missing limbs with something made of fiber or reed, some kind of artificial legs. And it's known there was a discovery in the year 2000 at an archaeological site of an Egyptian toe made of wood and leather. At first there was some debate about whether this was just for looks, it was just a for show, but it turns out that they believe that the way it was embalmed with the body, that it was actually used as a toe for balance and walking. Somewhat later, around 1000 BC, the Indian sacred Rig Veda, the book of hymns, mentions a prosthesis fitted to Vishpala, who was a female warrior, sometimes interpreted as a horse, in most cases interpreted as a female warrior who lost her leg in battle. And she was fitted with a leg of iron by the people that she was fighting to protect. That's the first written mention of a prosthesis. And later, between 700 BC and 400 BC, the Etruscan civilization in northern Italy, in present-day Tuscany, developed false teeth. These were teeth that were made from either human teeth or animal teeth. And you can see in the figure in the bottom left, there's actually a jaw from a human that had these teeth. And the two other pictures are modern-day representations, remakes of these Etruscan false teeth. And in 500 BC, the Greek historian Herodotus describes a prisoner cutting off his foot in order to escape his ankle chains, and later replacing that foot with a wooden substitute. So how is it that for thousands of years we've had these prostheses? Well, necessity is the mother of invention, and while there was no necessity thousands of years ago for a laptop or a cellular phone, it's pretty clear when you look at someone who's missing a leg that there's an opportunity to improve that person's life. And it's pretty clear that a piece of wood or some kind of a device to help that person stand better, walk better, is a good idea and a good invention. It's fairly low tech. So these things have been around for quite a long time. But of course, we've modernized and we've improved upon these implants. So let's look at what's been available more recently. We have prosthetic arms, legs, a prosthetic eye, and these things are available. They're obviously much improved from thousands of years ago. The arm in the picture is attached to the remainder of a person's arm and can be used to pick things up. Sometimes these things have grippers. These grippers are often controlled by a cable that goes around to the person's other shoulder, and by moving their shoulder, they change the tension on that cable and can grip and release. So there's some functionality. You can see the different types of legs, one for standing and walking, another set of legs with a composite structure that can be used for running. And while they look very little like human legs, these composite legs perform extremely well for the specific task of running. The artificial eye, the prosthetic eye, is a replacement when someone is completely missing an eye. It looks natural, but it has no function. So it's a replacement of the look of an eye, but not the actual function. So today we're going to talk about some newer, more advanced techniques, some new technologies for developing prostheses to replace the function of a body part. One is more advanced prosthetic limbs that are actually controlled by the person, some robotic moving limbs that can add more function. Another is an artificial heart. People have talked about this. This has been on the news in the past. We'll look into some of the design issues of an artificial heart and other types of heart devices. Neurostimulation. Now we think about these other prostheses as replacing a distinct body part. When we stimulate the brain or a nerve, we're actually shutting down a part of the brain that's not working correctly. So it's, in a sense, restoring some of the function of a small part of the brain. And then there's prosthetic hearing, the cochlear implant for the deaf. That has been tremendously successful. And based upon that technology, there's research on prosthetic vision, a retinal prosthesis or a cortical visual prosthesis for the blind. Finally, we're going to discuss some of the technical issues, some of the engineering and science problems to develop these types of prostheses. First, let's start with the controlled prosthetic limb. Here we have a hand, the limb by Touch Bionics. This is a limb that is obviously much more advanced than the gripper that has been around for some years, for decades. This limb has independent fingers and joints. It looks fairly natural. It looks like it has fairly natural motion. There's another one of these, the DARPA arm, and this device can move, as you can see in the video, this device can move in a wide variety of ways. In this case, it's being controlled by a person wearing a glove, so they're controlling its motion in that way. This arm has 22 degrees of freedom, 22 different ways that it can move, moving fingers, different joints, rolling the thumb across the palm. And it has tremendous dexterity. It can pick up objects, it can pick up delicate objects without crushing them. The question is, how do you control this? The early robotic arms were controlled by electrodes on a person's muscles, maybe the muscle of the chest. You put EMG, electromusculogram electrodes, on the chest, and when you flex that muscle, you can raise or lower an arm, open or close a robotic gripper. But clearly, putting some electrodes on one muscle is not going to give you enough information to control a limb with this many degrees of freedom, with this much flexibility. We need a lot more information. The question is, where can you get all this extra information to control an arm that's this complex? And we can get that from the human brain. We can actually implant microelectrodes into the motor cortex of the human brain. And when someone thinks about moving a limb, we can record the thought signals from that motor cortex, from those electrodes, and interpret them. And we can get a lot of information about that, use that information to control a robotic arm. This is fascinating research, and there are at least a few groups in the country who are really moving this work forward. One of them is BrainGate technology, the BrainGate device at Brown University and Cyberkinetics. This group in the picture there has implanted these penetrating microelectrodes into the motor cortex, and in a moment I'll show a video of a person with this device who can actually move a cursor and move a hand. It's fascinating work. The other group is the Motor Lab at the University of Pittsburgh. They have implanted a similar device into the motor cortex of the brain of monkeys, and they can extract information from those motor signals of the monkey to move a robotic arm around. So first, let's look at this video.
Matthew Nagel was paralyzed from the neck down after being stabbed several years ago, but technology gave him hope. He was one of 4 testing BrainGate, a new technology where a chip is implanted in the brain that picks up electrical impulses. A computer then interprets those impulses as actions. The chip is implanted just beneath the patient's skull and is only a few millimeters square. Here's Matthew playing a computer game. He's not using a mouse or a joystick, rather he's thinking of where to move the paddle. All thoughts are electrical impulses, and after extensive research and testing, a computer has been trained to decode those impulses and create the corresponding actions.
Now close it.
Now close. Nice. Open. Not bad at all.
So here we can see that this person can actually open and close a robotic hand. Similar in technology to the gripper, but using his brain, using the motor cortex of the brain. He can also move a cursor across a screen, which means you can control other things in that way. The other research group that's working on this is at the University of Pittsburgh. They've implanted, as I mentioned, this device, these electrodes, into the motor cortex of a monkey to control a robotic arm. They've successfully extracted several degrees of freedom, and they've used the monkey's signals to control a robotic arm that rotates and twists and can grab a treat off of a stick, and the monkey can eat it. The monkey's arm is held still, and it actually grabs the treat, eats it. They put the treat somewhere else. He reaches and grabs it and eats it. So using the monkey's hunger for these sweet treats, they actually provide the motivation to control this robotic arm with many different degrees of freedom. Fascinating work. Let's talk a little bit about the artificial heart. This is a fairly well-known implant, a fairly well-known prosthetic device, and it's used to pump the blood around the body just like the regular heart would. This particular device completely replaces the heart. You remove the heart, put this device in there. There are a number of technical challenges here. First of all, it takes a lot of power to move all that blood around. That power can't be supplied from a small implanted battery. Another heart device is the pacemaker. That's a very small device. It has a battery that gets implanted for 5 years. It electrically helps the heart along, but that battery lasts for a very long time. In this case, you're actually replacing the mechanical power of the heart. And in order to do that, you need to deliver power from outside the body. At the end, when I discuss the technical issues, we'll talk about how you can deliver power from an external battery into the body to power something that's this complex. Some of the other concerns with a device like this is that the blood isn't just a liquid. You've got cells, red and white blood cells in the blood, and you need to make sure that the valves, the metal parts that are moving in this device, don't damage the blood cells. If you damage the blood cells, it's defeating the purpose. The other problem is that there are platelets in the blood which will congeal at a wound and start clotting. You need to make sure that a device like this artificial heart, doesn't allow those platelets to start forming a clot within the heart that can break loose, go to the brain, and cause a stroke. Let's look at a slightly different alternative to the artificial heart, and that's a left ventricular assist device, an LVAD. This device leaves the patient's heart in place, and instead, it replaces the function of the left ventricle. It helps the left ventricle by taking blood out of the left side of the heart and pumping it into the aorta. So the right side of the heart still collects blood, pumps it through the lungs and back into the heart, but this LVAD device pumps the blood up into the aorta and through the rest of the body. Obviously, the same concerns apply here, that this is a power-hungry device compared to some of the other devices. It needs to receive power from outside the body. In fact, you can see in this figure there's an external battery pack and a set of coils that wirelessly delivers that power. And also the same concerns apply about damaging blood cells and not allowing clots to form. Let's move on to the brain. We heard about a technology that can sense signals in the brain in order to control a device, but let's look at ways of sending signals into the brain. This is neural stimulation. And what these devices do, they're just like pacemakers. They're small titanium devices with a battery that deliver electrical currents to the body. In this case, they're used to deliver electrical currents to the brain or to a nerve. Sometimes these things are used to treat chronic pain, depression, Parkinson's disease, epilepsy. They can also treat urinary incontinence. I've even heard of a case where it treated Tourette's syndrome. These things are used in a wide variety of applications, and they mostly deliver stimulus to a nerve or to the brain to interrupt a faulty part of the brain's signals. In Parkinson's disease, there's a part of the brain called the subthalamic nucleus, which is the source of an erroneous signal which causes the tremor of Parkinson's disease. And when you stimulate that part of the brain, it can actually stop the tremor. I'm going to show here a video that shows a number of people with these kinds of problems that have been treated by this kind of deep brain stimulation. You have before and after videos, just a variety of people here with tremors or dystonia, which is a crippling clenching of muscles. And these kinds of stimulations in the brain can actually stop these erroneous signals and can allow a person to go about their life much more normally. searching on a website like YouTube for deep brain stimulation and something like Parkinson's disease brings up dozens of these videos. They're fascinating. I recommend looking for more of these. You can spend all day just looking at these videos. Tremendously interesting stuff. Now, the question here is, we know when we put in an artificial heart where it has to go because we know where the heart is. We know when we put in an artificial limb how to surgically attach it. How do you do this deep brain stimulation? This is, as the name would imply, very deep in the brain. You're targeting a very small area. You're putting in an electrode that has to go down from the top of the skull. They actually drill into the top of the skull, put the person's head in a stereotactic vise, for lack of a better word, and the surgeon will actually feed this electrode down into the brain. The question is, how do you know when you get to the subthalamic nucleus or the internal globus pallidus? And the answer is, these people are awake during the surgery. The patient is lying there completely awake, and when they introduce the lead, the electrodes, to the part of the brain where they think that it should be to stop this tremor in Parkinson's disease, they actually start pulsing the lead. And if the patient's hand keeps moving, they're in the wrong place. So they move the lead down a little further, deliver the stimulation again, and when the hand stops moving, they know that they're in the right place. So these leads, this deep brain stimulation lead, is placed in the brain while the patient is awake, which is fascinating and a real surgical feat. Let's move on to a different type of an implant. We've heard about trying to introduce signals to the brain, but only to interrupt a faulty part of the brain. Now let's try to introduce real information into the brain for people who are deaf. And the way hearing works is sound approaches the ear, sound which is changes in air pressure, and those waves of air pressure strike the eardrum. The head of the eardrum actually moves back and forth and moves the bones of the middle ear, hammer, anvil, and stirrup of the middle ear. Those bones conduct those waves to another thing that looks like an eardrum, the oval window of the cochlea. This is another membrane, another window that vibrates with those bones and creates a vibration that propagates through the cochlea. There's fluid in the cochlea that vibrates, and there's a membrane that vibrates. Attached to that membrane are these very small hair cells, and when they vibrate, the hairs deflect, and it creates a little electrical nerve signal that is then sent to the neighboring nerve, the auditory nerve, which goes back to the brain. Different parts of the cochlea carry different frequencies of sound. So very low frequency bass sounds actually resonate way out at the tip, the very small tip of the cochlea. And it vibrates more at that location, so those hair cells fire and those nerve cells fire. And that's where the low frequency sounds are heard. And when high frequencies come in, right near the base of the cochlea, the thickest, widest part, that vibrates, those hair cells vibrate, those nerves carry signals back to the auditory cortex of the brain. Now, a number of things can go wrong to cause deafness. Some of those are conductive losses, conductive hearing loss, which damages the bones or somehow allows those bones not to conduct the waves to the cochlea, or sensory neural hearing loss, where those hair cells of the cochlea die away and are no longer there to transduce the sound, so the nerves aren't receiving any input. When this happens, the best treatment is a cochlear implant, and this is an electrode array introduced to the cochlea, much like the deep brain stimulator lead, that electrically stimulates the cochlea at different places. Let's look at how this works. This contains a microphone attached typically to the outside of the eye or outside of the ear, right behind the ear. Looks kind of like a hearing aid. The sound from that microphone is sent to a hearing processor, a voice processor, sound processor, typically attached to the belt of the patient, which also includes a battery. The information from this processor is wirelessly transmitted along with battery power to the implant. The implant has a little chip which then electrically stimulates different places along the implanted leads in the cochlea. It separates out the sound by frequency and stimulates different places in the cochlea based on the frequency of the sound. And this allows people to hear. Thousands of these have been implanted over the years. They work fairly well. It's not the same as natural hearing. It takes a little getting used to, but people have learned how to use these and can really function quite well. Now, that is the cochlear implant for the deaf. Now let's talk a little bit about blindness, another field, and the field that I work in. If I were to say that there are cells in the eye that transduce light into electrical nerve signals, and that there are diseases that kill off those cells in the eye, but leave the nerves intact, you would think that sounds very similar to the death of these hair cells in the ear, and that maybe something very similar to the cochlear implant could be used to treat these forms of blindness. So let's talk about the visual prosthesis. This delivers electrical current to the retinal nerve cells in much the same way that the cochlear implant delivers electrical signals to the auditory nerves. This treats degenerative forms of retinal blindness like retinitis pigmentosa and macular degeneration. Now, this device differs a little bit from the cochlear implant because it must be very, very small to sit on the moving eye. It must be attached to the eye within the socket. And it also must have a very large number of stimulating channels. Cochlear implants for the deaf have 16 to 24, typically, stimulating electrodes, stimulating channels. And that works fairly well for hearing. But to create an image, your 1 megapixel camera has 1 million pixels. Many images have 1 million pixels. And yet, imagine going from 10 or 20 or 24 channels to 1 million. It's just technically infeasible. So we're trying to ramp that up to dozens or hundreds of electrical pixels to create a visual prosthesis. Let's start and talk a little bit about how vision works. We have the eye. Light comes in through the lens in the front of the eye and falls on the retina, the thin layer of tissue that goes across the entire back of the eye. That thin layer is actually built backwards from how we might expect. Light passes through several layers to hit the photoreceptors, the rods and cones at the back of the eye, which transduce that light into nerve signals and propagate it back forwards to the nerves which form the optic nerve and go back to the brain. In these cases of degenerative retinal disease, the rods and the cones die off. And so what we do is introduce an electrode array, much like the electrode that stimulates in a cochlear implant, either in the subretinal space or sometimes on the front of the eye in the epiretinal surface. And we use this electrode to stimulate, to deliver pulses of current to the nerves. This would work in the following way. A patient would wear glasses with a camera, an image is collected by those glasses and sent to an image processor, much like the sound processor. That image is then transmitted, the image data is transmitted to the implant along with the power, and then there's an electrical stimulation. The implanted electrode array stimulates the retinal nerves to create a percept in the person's brain. And this is kind of a pixelated scoreboard image. There are a number of different types of these visual prostheses. We see epiretinal prostheses that go in from the front of the eye and sit on front of the retina. A subretinal prosthesis, which comes in from the back of the eye, sits between layers of the retina. Or a cortical visual prosthesis, which actually sits in the brain, in the visual cortex of the brain, and stimulates the brain to try to deliver information in that way. Let's talk a little bit about the challenges in developing these types of prostheses that we've talked about. We've talked about a wide variety of prostheses. They share some of the same challenges. There's surgical challenges, biological, electrochemical challenges, electrical, and mechanical. And I'm going to talk about each of these. Each has its own problems, each has its own engineer or scientist focusing on it. In the surgical issues that we look at, one is place the electrodes and the device safely and securely. We talked about this deep brain stimulation. It's a real challenge surgically to place that device where you want it. And then ensure that patient movement won't dislodge the device or the array. Here we see, in my work, the subretinal implant slides in from the back of the eye. You have to cut through 1 millimeter of tissue and be careful not to cut through the 1/10 of a millimeter of tissue that's right beneath it. So we need to lift the retina out of the way in a very careful way. And again, you see just how deep in the brain that deep brain stimulator goes. The deep brain probe goes inches down into the brain, quite far. Let's talk about some of the biological challenges. You're putting a foreign object in the body. The foreign object doesn't really want to be in the body, and the body doesn't really want that object there. So you need to make sure that the materials are biocompatible, which is to say the body doesn't react badly to having that material there, and ensure that the materials are biostable, which is to say make sure that those materials don't react badly to being in the body. So on the one side here, we see an example of biostability and lack of biostability. This is a thin electrode array that's been soaking in physiological saline at elevated temperature for a long time. And what happened here is these plastic materials have actually just delaminated, fallen apart. Doesn't look good in the bottom picture. In the top picture, we see a different material, different set of materials, different sandwich of materials that has lasted extremely well, that has held up quite well in that environment. In the picture on the right, we actually see an electrode that is implanted into the tissue, and we've taken a tissue sample. And you can stain these things, do all kinds of physiology tests and anatomy tests, and make sure that the body isn't reacting badly to the implant that's in there. And in this case, you can look and see if mechanically that electrode has torn through the tissue, and it is actually not in this case. It's settled down quite nicely. And you can look for scar tissue that builds up along this device. In some implants in the brain, you put a penetrating electrode in there, and it's a real problem. Scar tissue will build up over time and change the electrical properties of that electrode in that place. And in the case of some electrodes in the retina, in my field, we happen to be very lucky. The retina will actually not react nearly as strongly, so there's very little scar tissue. Let's look at the electrochemical challenges that we see. We're putting electrodes in tissue, and they need to stay within what I call the safe limits. So fundamentally, an electrode is a piece of metal, and metals will conduct electricity by moving around electrons. The body, on the other hand, is a bag of saline, effectively, and will conduct electricity by moving ions back and forth. At an electrode tissue interface, we actually need to have an interface between these two very different types of electrical conduction. And the way that we do that is by reduction and oxidation chemical reactions. This is also used in electroplating. So if you do this the wrong way, you can electroplate an electrode. You can create oxides that float away into the tissue. If you stick a piece of gold metal into the body, we think of gold as fairly non-reactive. But if you put enough current through it, you can have gold oxides floating through the body that damage the electrode and could potentially damage the body. So we need to pick our materials very carefully. We, in the retinal prosthesis, use iridium oxide film electrodes. Other people use platinum or a platinum iridium alloy. There are a number of different electrode materials that will allow this kind of reduction and oxidation reaction to be done reversibly in a way that can stimulate the tissue but not damage the electrode and not cause harm to the patient's tissues. Of course, one problem is that any electrode material, no matter how good it is, has a limit above which you will cause new chemical reactions that will damage the electrode. So here we see a couple of types of electrodes. These are iridium oxide electrodes under a microscope, and also waveforms that electrochemists use to determine how much charge can be safely delivered that will inform the electrical designers about how to design the circuits to safely use those materials, to safely stimulate with those materials. So there are electrical challenges to safely stimulate with those materials. In particular, do not shock the patient. This would seem to be fairly obvious, but there are a lot of ways that things can go wrong, a lot of ways that an engineer might not think about that can really cause some damage to the patient. So we have to think about what kind of failure modes can happen and try to build in extra safety features that can try to protect against those failure modes. If one thing goes wrong in your implant, you can't allow that to cause damage to the implant or to the patient. You need to be able to accept one mode of failure and have a separate safety feature that protects against it. And the second, something we've talked about a couple of times here, is power. We said that those heart devices, the artificial heart, the LVAD device, the ventricular assist device, take a lot of power, and the cochlear implants and these retinal prostheses are very, very small, too small for a battery. And so we must transmit power from outside the body. So here on the left, we look at the voltage across an electrode. And there are a couple of places during that stimulation, a couple of times when we want to very carefully monitor that voltage and use our safety features to detect whether that electrode is still operating in its safe region. And if it's not, there are other safety features that will either correct for that or take that electrode out of the picture. And in a retinal implant with hundreds of electrodes, you can afford to have an electrode fail and just be removed from operation. On the right, we see how we are going to actually deliver this power to a device. We saw in one of the LVAD pictures there was a coil. We're actually wirelessly transmitting power from the outside of the body to the inside of the body. If you take a loop of wire and send an alternating sinusoidal current through it, you create a magnetic field in space that just passes through the body. If there's another loop of wire inside the body that's exposed to that magnetic field, you will induce an alternating sinusoidal voltage on that coil. And that is then rectified by some circuits and used to create a power supply for the cochlear implant, the retinal implant, the left ventricular assist device that powers that device and wirelessly delivers power from an external rechargeable battery to the very small internal device. So the final set of challenges that we're going to discuss are mechanical challenges. When you place a device in the body, not only can it cause biological challenges, not only can the materials cause biological reactions, but mechanically you can design a device that when the moves around in the body that damages the body mechanically. Obviously we need to protect against that. So we need to ensure that the implant does not damage tissue over time and that the implant device is not damaged by tissue. If you have an electrode or a lead that's very thin in a body part that's moving, that lead needs to be flexible enough that it can flex tens of thousands of times without failing, without causing damage to the implant itself. And the final issue is that the implant itself, if it has any electronics, if it has any electrical components, needs to be hermetically encased. We think about these devices as having silicone or plastic on them somewhere. That plastic does not prevent water from getting in there. We think about plastic as being waterproof. Sure, it works fine for most applications. But when you put a device inside the body, inside a saline environment constantly for a decade, and enclose it in some kind of a polymer, plastic, silicone, you will actually get water vapor. Water will turn into a vapor and penetrate right through that polymer, condense on the other side, and cause damage to the electronics over a span of years. So what we use instead is a titanium hermetically sealed case. Hermetic means airtight, not watertight. So it prevents water vapor from getting in there. We use a titanium case, as we saw with these neurostimulator devices. It's the same as in a pacemaker. And these sorts of devices, these neurostimulators, pacemakers, have 4 leads, typically 2, 4, sometimes 8, that come out of this titanium case through a feed-through, through a ceramic part that allows those pieces, those wires to come out independently, but which blocks this water vapor from getting in there. This is tremendously important. And for a cochlear implant for the deaf, now instead of 4, we need 24, 28 of these hermetic feed-throughs. So you can imagine for a retinal prosthesis, for a vision prosthesis for the blind, you want hundreds of these very small feed-throughs to come from inside that hermetic case to outside, where you're stimulating and delivering that electrical current to the tissue to create the image. This is a tremendous challenge in that field. And to conclude, I wanted to say that this prosthesis technology has advanced tremendously from the days of these Egyptian toes and Etruscan teeth to where we have composite legs that help people run. We have these eyes that look natural. And in the last decade or so, this technology has advanced much, much more. It's accelerating. Ray Kurzweil talks about the singularity, where technology may take over and where devices can start designing devices. I don't know if I believe in the singularity just yet, but it's clear that technology is accelerating, that we're going to make progress faster and faster on these devices, and to add more functionality to the patients who need these kinds of devices. The future of this field is yet to be written. So starting with the Egyptian toe, we've come a long way to all sorts of different devices that are available today. But looking into the future, there are a lot of unknowns. All we know is that advancement is going to be rapid, and there are a lot of exciting things that are going to be happening. Thank you. Yes.
You said you basically read what's happening in the brain to control some of these devices. What would happen if somebody was dreaming?
Wow. So the question, a fascinating question, is when we use these brain implants to extract thoughts, to control a motor cortex device or something like that, what would happen if someone were wearing this device, had this device active, while they were asleep and dreaming? That's just a fascinating thing to think about. I mean, you know that when you're dreaming, you're thinking about running through a field or being chased by someone or whatever it is that you're dreaming about. And the only reason that you're not flailing in the sheets is that your body actually prevents motion. It actually kind of stops your limbs from moving so that you can actually stay asleep. But clearly, your brain is thinking about it. And clearly, your motor cortex is going to be sending these signals to try to make your body move. So if someone were asleep and wearing this motor cortex device and connected to a robotic arm, I think that the robotic arm would be moving all over the place as this person dreamt about moving it. Other questions?
So you basically you have to find a way to tap into that part of the brain that does disconnect your limbs from your brain while you're sleeping.
So the question is then, do you need to find the part of the brain that shuts down the motion of your limbs while you're asleep? Well, that would be tough to do. You could do that. Personally, I'm not completely sure where in the brain that's regulated. It would be easy enough, though, to just turn off the device or turn off the robotic arm while you were sleeping. But trying to find the part of the brain that regulates that and activate it, or to somehow take the motor cortex outputs from the brain downstream of that part that regulates, part of the brain that regulates your limbs while you were asleep would be one way to go too. It's much more difficult than just turning off the device though. Yes?
Hardest thing in that, and the second.
So it's a fascinating question. This is a very interdisciplinary field. It's the merger of many different kinds of engineering with many different kinds of science, biology, neuroscience, and surgical aspects. So the first question is, what are the most difficult parts, the most difficult challenges to making this interface happen? And it's really that you need to put together a team of people from all of these different aspects, from all of these different fields, who can communicate with one another. In the end, after several years of working on it, or after decades of working on it, everybody learns a lot of everyone else's business. I know a little bit about surgery and biology and neuroscience. We just pick these things up working together, but no one person can know enough to design something like this. It's just much too complicated. So the hardest thing is putting together a real team of experts. And it's sometimes difficult to find all of the experts that you need in one location. So you end up sometimes working with people remotely, and that kind of communication, getting everyone in the same place occasionally, getting everyone to communicate on a design that's this complicated. Some of these things have a lot of moving parts, a lot of mechanical, a lot of electrical things going on, and a lot of biology. And everybody needs to be able to communicate their expertise at meetings together and somehow come up with a design that satisfies everybody's different constraints. And this is impossible to do the first time. So there's a lot of iteration. It takes a lot of patience and a lot of teamwork. We need to get back together from time to time, find out what's not working, and change direction from time to time. It's a real challenge putting together a team with that kind of expertise and getting them all to work together in an efficient way for a long time. The second question was in reference to the mention of Ray Kurzweil and this singularity, this acceleration of technology. Do I think that we will really get to a point where these prostheses start to really restore some real useful function? And I think so. I think it could take a while. But I think that technology is accelerating rapidly, and we learn from the patients just as much as we, the scientists and engineers, learn from each other. So the cochlear implant concept came up a long time ago. People started stimulating within the cochlea, trying to produce sound, trying to produce hearing, and the sound was terrible. It took a very, very long time for patients to understand and learn how to use it, and then to give feedback to the researchers who could improve the stimulations, improve the sound processing. And as an iterative process back and forth over time, patients have learned how to use it, and scientists and engineers have developed better devices. And this is going to continue with the BrainGate and the motor lab technology. Sensing signals, sensing this many signals in the motor cortex is tremendously difficult. And the electrodes will improve over time. The sensing technologies and amplification will improve. And then the computer algorithms for extracting data from these signals will improve. And these sorts of devices will get better. The retinal prosthesis for the blind, a company called Second Sight entered human trials with 16 electrodes. They now have 60. And they and other groups are working on hundreds of channels. Obviously, for real vision, we'd like to see thousands or more electrodes to actually stimulate the retina, stimulate the brain, and this will come as technology advances over time. I believe that many of these devices will drastically improve in the years and decades to come. I think that they really will never completely replace what biology gave us originally, but I think that they will come very close.
With space flight and so on, you know, the damage to the human body is just overwhelming. You almost need a...
Yeah, you're going to have to edit my reaction as I think about this one a second. So that's another fascinating question. As we try to explore space, as we try to send ships farther out and get exposed to the radiation and all the damage that can occur, we may want to send robotic probes, and we may want to send more autonomous robotic devices out to explore space. And the question is there a way, or do I see a future for trying to infuse human minds, human thoughts into a purely mechanical device, so a robotic with true human brain function? And I have to say, I think that's a bit farther out than some of these implant advancements. I believe that we'll have more autonomous, purely robotic, purely mechanical devices that can start to use machine vision and other sensors to understand their environment and to start to make decisions about how to interact in their environment. There's a lot of that that's underway now. Robotic cars driving around in races, robotic submarines searching for things, and I think that there's a lot of development in that area, and that will improve something like true human thought in a robotic exploratory device, in a mechanical robot, I think is still quite a long way off. I think what will happen is an autonomous robot that can sense its environment and react to its environment, and then gets very occasional input from humans back on Earth to correct its action, to reprogram it. Remember, something this far away can't be controlled in real time because of the lag in sending radio signals, but a person could analyze how the robot is doing and correct its autonomous programming to help it react better.